All right. Today we will be presenting the classification algorithm comparison for predicting employee attrition by Jonathan Miller and me, Lucas Bowker. As far as kind of what we're going to be discussing here, we're going to start with an introduction to the problem and go over some related work to kind of frame our problem a bit better. Finally, for the actual work done, we'll be covering both pre-processing, model comparison, development, and results. And finally, we'll resolve this with a conclusion, including some future works and our demonstration. So our key problem is, what exactly is employee attrition? Well, it's losing employees. Most notably so, it's losing important employees. Why? Well, it can be very problematic when you lose an important employees, such as having a high rehiring cost, retraining cost, severance pay, and many other factors, maybe such as how long it takes to train some individual back up to the level they should be at. The question is really, is this, given some data set, is this predictable or is it completely random? So that's what we're going to try to solve. Here's the data set we use is the IBM HR Analytics data set from Kaggle. This data contains 35 different attributes, 1,470 records, and various data types, including numerics, booleans, and factors, such as whether an employee travels frequently, rarely, or never. And our end goal is to provide predictions using two custom models to the employer as to whether an employee is likely to quit or not in a convenient GUI format. Some of the related works that we covered include a work by Tolinar, which involved prisoner recidivism. Basically, what this is whether a prisoner is likely to come back to prison after leaving after their mandatory sentence. And why this one is so closely related is actually some of the prediction models and data they used is very similar to ours, in that they used a logistic regression model with many different hyperparameters and some boosting as well to try to provide a good prediction as to whether a prisoner is likely to go back to prison or not. As far as Watlington goes, they covered teacher attrition on more of a fiscal side of things. They found that each teacher cost $14,370 when they quit. Now, Kim covered a slightly different attribute set in that they covered the quitting or the attrition of students. What leads to student quitting can be many, many different factors, but oftentimes those factors aren't quantifiable. And what we're hoping to accomplish is to use our more quantifiable data to predict whether an employee will quit or not. On to pre-processing. So to begin with, there are just far too many features. Why are there far too many features? Well, this is mainly because we don't want the employer to have to type 35 different numbers to provide a prediction. It doesn't make sense. So our initial thought was, well, maybe we could use some type of dimension reduction, but this doesn't really make sense, mainly because something like PCA would, principal component analysis, would still require you to input 35 different features, even if it's reduced to, say, 10 for the actual model. So that wasn't really what we were looking for. So we moved on to feature selection, where we use majority vote of 5 feature selection techniques to narrow down features. Some of these feature selection techniques include ANOVA, chi-square, and a few others. And what this ended up doing is it narrowed down our feature set from 35 down to 10, which is a much more reasonable amount of features to be inputted into our GUI. Finally, we did a little bit of one-hot encoding for some of the variables to help the models utilize them correctly.
So on to the model comparison. We're comparing two models that were provided pre-made from scikit-learn, and those specific two models were logistic regression and decision tree. And as we can see from this chart, they perform very similarly, at least with accuracy. So the accuracy is the leftmost pair of bars on this bar chart. And you can see that the accuracy bars are very, very, very close. We actually did a statistical analysis on those bars, or at least the accuracy or error values. We found that they are not significantly different. There are some other differences among the other measurements here, such as recall, precision, F1 score. One thing that's interesting is that logistic regression has a much, much higher recall, but decision tree has a higher precision. And if you actually look at the F1 score, because the decision tree is sort of better at, or at least is consistently good at both things, both recall and precision, it actually has a higher F1 score than logistic regression. So just to show a little bit more of the outputs from these models, here is a decision tree. I'm sorry, the confusion matrix for decision tree and logistic regression. And you can see that the decision tree, the top right box has a 9, and the logistic regression, the top right box has a 2. That means that the decision tree had a few more false positives than the logistic regression. And similarly, you can see that the opposite is true for the bottom left box. The decision tree had a few fewer false negatives than the logistic regression. And just to show even more outputs, we have the KS plot and ROC curve. You can see that the shape of the two here is actually quite similar. The AUC for the two models is shown sort of as a number on the bottom chart. You can see that the AUC for logistic regression is actually higher in this instance. Now, one thing that's interesting to note is that the KS plot has sort of a difference between the two, which is how smooth or how many data points there are on that plot. And so the logistic regression plot has a whole lot of data points on the KS plot, but the decision tree is sort of bumpy. And the reason for that is that what the KS plot is doing is it's showing the output probabilities of the models. So logistic regression can have any float between 0 and 1 as an output probability, but the decision tree's output probabilities depend on what leaf there are, leaf the data point went to. So there's only a finite number of leaves, which means that there's only a finite number of points that can go onto this graph, which is why that plot sort of looks different between the two.
All right, moving on to our implementation of the custom decision tree. So we decided upon implementing 3 different hyperparameters, including max depth, max number of features at each split, and we only included Genie support due to time constraints. Now, as you can see on the right here, the initial implementation did not work so well. Now, the key part of this issue in identifying this issue was realizing that splitting at the best index was not necessarily the best choice. This would be perfectly fine if all the values in each column were unique, but the problem is many of them weren't. Take, for example, some binary value. We could use our class label, for example. They either quit or they didn't quit. Now, the initial implementation of the decision tree could arbitrarily split in the zero. If it's 5 zeros a row and 3 ones, it could arbitrarily decide to split in the middle of the zeros. That didn't work, and that's what caused our issue on the right. After fixing this and splitting by value instead, we had much better results. All right, and on to custom logistic regression. So as far as the implementation goes, we implemented a gradient descent solver. We implemented this as a set of hyperparameters, including learning rate, learning epochs, and number of batches. However, as seen on the right, this was initially not going so well. The problem lied in convergence, in that the SGD algorithm previously implemented did not converge and produce these erroneous results. The primary issue was the scale of the variables. We had to fix this so that, for example, income didn't overly influence the results. After scaling these variables, it ended up working much better, as we'll see soon.
So the outcome from these models, we saw that they were very, very similar to the pre-made models, which sort of makes sense. They are the same algorithms. We can see again that they have very, very similar accuracy, which again is the pair of bars on the left. And again, we did a statistical test and saw that the difference between the two models were not significantly different. One thing that is interesting to note as an outcome from these models is that the recall precision F1 score are now even more similar to each other than we had before. And so just to show you the confusion matrices again, so we can see here that there's actually only one difference between the two models, and that is the decision tree had one fewer false positive than the logistic regression. This is quite interesting. We actually thought that this was perhaps a flawed result, and that maybe we had run the same model twice, but no, they are in fact this close to each other, given our implementations. So similarly, here is the KS and ROC curves for those two models. And now you can see that upon further inspection, they're not performing quite as well as the pre-made models. And our assumption for why that's the case is because the pre-made models had far, far more hyperparameters for us to tune. However, our implementation had fewer hyperparameters, and therefore it couldn't find as precisely good of a model for this specific task as the pre-made models. And so you can see like the decision tree ROC curve is a little flat. The AUC there is 65, which we were previously operating somewhere in the 75 range. And so the outcome from all of this, our ending closing thoughts is that attrition is not fully random. We did have a slightly higher than chance prediction accuracy. And again, we could have gotten even more accuracy if we had included more features or perhaps more sophisticated models. One thing that we also saw is that decision tree and logistic regression are not significantly different. They perform very, very similarly with everything that we gave to them. And again, one of the most important outcomes from this project is the GUI that we've developed for these predictions, which we're going to show here in just a second. So our future work is to analyze this class imbalance in more depth. So there is a sort of slight class imbalance. There are more people that stay at their jobs than there are those that are lost to attrition. And that could have had some effect on our results. We're not sure because we didn't really analyze that class imbalance in more depth. There are many, many approaches, many, many things to research in that field, in the field of classification when there's a class imbalance. But for this specific project, we focus mostly on model comparison. And again, some future work may include more sophisticated models and more hyperparameters for those sophisticated models, which would get you more performance on this data set. But most importantly, what really needs to be done for future work is to test the generalizability with data from other companies or other fields. So our data set was from one company, IBM. We are simply analyzing that data set to try and get our highest prediction accuracy, but we really have no idea how much our insights, our results, uh, correlate to the results that would come from other fields. We just have no idea how similar two different fields are. So now we're going to show off the GUI that we've implemented. That GUI is here. So what we can see is that we have a entry form on the left where we can show, we can give our models the input data for a given employee. On the output, we have two charts. Each one of these charts represents, it's sort of like a KS plot. It shows what were the output probabilities that the model predicted for the training set. And so you can see sort of how uniquely high chance of attrition at a specific employee. How similar are they to other employees? And where do they fall on the histogram of probability outputs? So our GUI here outputs the attrition probability of both of the different models, and it sort of also includes the class prediction of whether or not that specific model predicts attrition. So what we can do is we'll start out with a very, very simple input. We'll put in all zeros, and then we'll simply say that the employee uses overtime. And you'll see that this is a very, very high chance of attrition predicted by both models. Both models put this hypothetical employee in the very far right of this graph, which means they're in the highest of attrition range. And that sort of makes sense. This employee is being paid nothing. They have no years of experience in this current role, and they are the lowest level on the totem pole, and they are using overtime. So that's quite abysmal. But we can imagine that we might pay this employee more, so we'll give them a good salary. And now neither of the models predict attrition. And so we can keep changing things. For example, what happens if they travel frequently? That bumped up a little bit higher on the logistic regression. And one thing that's interesting to note is that the decision tree did not change its prediction. And part of the reason for this is that to change the prediction of the decision tree, you have to find a new leaf. It's not very discrete. So we'll have to change some sequence of things here that will put us in a new leaf for the decision tree to predict a different outcome. So we can also change other things. We might try maybe they've been at this job for a bit longer. We can say what happens if they've been at this job for a super long time. See, now logistic regression says there's a 0% chance of someone being lost to attrition if they spent 100 years in the current role, which sort of makes sense. So let's say they spent 5 years in the current role. Maybe they're 30. Maybe they're level 2. We'll see what that looks like. A little bit higher. We'll say they don't travel frequently. And we could change all sorts of things. We could say what happens if they travel. They have to travel 1,000 miles every day to get to their job. Just regression says this is absolutely not going to work out. Decision tree very stubborn, still does not see this change, and that's because again, we have to change a specific sequence of things for it to pop into a new leaf. So that's our GUI, and it should be very, very simple to use. There's only 10 different attributes that need to be input, and the output is very clear. And hopefully, this would find use for employers to verify or to figure out which employees are at the highest chance of attrition. And that is all for our project. So thank you for watching.